Hey everyone, and welcome to this explainer. I'm absolutely thrilled you're joining us today because, well, we're going to unpack one of the most fascinating and completely hidden mechanisms that literally runs our modern world. We are going on a bit of a journey here. We're going to trace the flow of data from tiny, microscopic hardware logic gates all the way up to the massive global internet networks we rely on every day. Trust me, by the end of this, you are going to see the very device you're watching this on in a completely new light.
Okay, let's dive into this by looking at a remarkably common, everyday scenario. Picture your computer right now. You might have Skype open, waiting for a message from a friend. You've got a browser tab constantly refreshing Amazon, and maybe Netflix is streaming away in the background. All of this data is flying in from completely different servers, and it's arriving at your single device at the exact same time. So how on earth does your computer keep all this traffic from just colliding? How does it know for sure that a chunk of video data goes straight to Netflix and doesn't end up in your Skype chat? Honestly, it's a massive application traffic jam just waiting to happen.
To solve this little mystery, here's our roadmap for today's explainer. 1. The application traffic jam. 2. MUX and DEMUX defined. 3. The digital logic level. 4. Sockets and port addresses. And finally 5. UDP versus TCP demultiplexing. And hey, don't worry if some of that sounds a bit technical right now. We're going to use some really brilliant everyday analogies to make all of this crystal clear.
All right, let's kick things off with Section 1, the application traffic jam.
So, every connected device out there uses a 5-layer model to communicate. We're talking the application, transport, network, data link, and physical layers. When you send a message, say typing a quick reply on Skype, your data flows from the top application layer all the way down to the physical layer, where it actually travels out over the wire or your Wi-Fi network. But when your computer receives data, it does the exact opposite. It flows bottom to top. Now keep our scenario in mind. Data from Amazon, Netflix, and Skype is all hitting your device's single shared physical path at once. As that data travels up the layers, your computer's transport layer is suddenly faced with a massive sorting nightmare. It has to look at this crazy bottleneck and perfectly distribute all that incoming data to multiple different applications.
Which brings us to Section 2, MUX and DEMUX defined.
The whole process of solving this traffic jam relies on two fundamental actions. First up is multiplexing, which we usually just call MUX. This is simply the act of combining data from multiple devices or applications and sending it all through a single shared medium. You can think of it as a many-to-one action. Then we have demultiplexing, or DEMUX. This is the exact reverse process happening at the receiver's end. It takes that combined single stream of data and carefully separates it back out to its original intended destinations. So DEMUX is very much a one-to-many action.
And this brilliantly illustrates exactly what we mean using things you probably see every single day. Think of multiplexing like a busy highway on-ramp. You've got multiple different local roads feeding cars onto one single high-speed highway. Or think of an old-school cable TV wire. It's just one physical wire, but it's carrying dozens of different channels into your home all at once. That's multiplexing in action. Now, for demultiplexing, imagine walking into an airport terminal. Everyone arrives through the exact same front door, but then you get separated. First class goes one way, coach goes another, TSA pre-check heads to one line, and standard security to another. Or, going back to the TV example, your cable box takes that single multiplexed wire and demultiplexes it, splitting out MTV, the local news, or the sports channels so you can watch just that one specific stream.
Let's dig a little deeper now. Section 3, the digital logic level.
So at the absolute lowest hardware level, engineers build these tiny physical circuits called multiplexers. And they are governed by a very strict, kind of beautiful mathematical relationship. A multiplexer takes 2 to the power of n inputs and funnels them into exactly one output. Now, to decide which input actually gets to use that output, the hardware uses something called n select lines. Basically, if you have 4 inputs, which is 2 to the power of 2, you need exactly 2 select lines to manage that traffic. If you scale up to 8 inputs, well, you're going to need 3 select lines.
Let's actually look at how this logic works in a real 4-to-1 multiplexer. You've got 4 inputs desperately trying to get through one single output. The hardware relies on those 2 select lines we just mentioned. Let's call them S1 and S0. Because computers speak binary, these lines can only ever be zeros and ones. So if both lines are 0, the circuit physically switches to allow only input 0 to pass through. But if the select lines change to 0 and 1, boom, the circuit instantly switches to pass input 1 instead. This right here is the physical hardware foundation of data sorting.
It's just rapidly changing binary voltages, switching streams of data on a microscopic level, all happening in mere fractions of a millisecond. Let's move to and see how this builds as we jump into Section 4, Sockets and Port Addresses.
Okay, so the hardware can physically switch signals, but how on earth does the network actually know where to send them? Well, check out this number right here, 65,535. This isn't just some random figure we pulled out of thin air. This is the absolute maximum number of application ports available on your computer right this second. It's a 16-bit number, and it represents this massive, staggering scale of possible simultaneous communication channels that your single device can handle.
And these 65,000 plus ports, they are highly organized. The first slice, running from port 0 all the way to 1023, are what we call well-known ports. These are rigidly fixed. They're reserved by internet authorities for really crucial services. For example, anytime you browse a standard website, your data is using port 80 for HTTP. Port 20? That one's reserved specifically for file transfers. You can't just randomly decide to use these for whatever you want. The next slice is the registered ports, going up to about 49,000, and those are used by specific applications. And finally, the last slice gives us the dynamic ports. These are just temporarily assigned by your operating system whenever you pop open a new app or open a new browser tab.
All right, now we arrive at what I think is the most vital piece of this whole puzzle, the socket. Think of an IP address as the street address of your house. It gets the data to your specific computer. But once it's actually at your house, which room is it supposed to go to? That is the port address. When you combine Step 1, the device's IP address, with Step 2, the application's port address, you get Step 3, a socket. The socket is the ultimate delivery destination. It is exactly how your transport layer knows perfectly that, hey, this specific packet of data goes to Firefox, and that one over there, that goes to Skype.
And that leads us to our final section, Section 5, UDP versus TCP demultiplexing. Out on the wild internet, your data is primarily transported using one of two main protocols. First up, we have UDP. UDP is connectionless, which basically means it's incredibly fast, very simple, and honestly a bit loose. When a UDP packet arrives, your computer looks at just one single thing, the destination port number. If the packet says it's for port 5000, the computer just drops it right into the socket for port 5000. No questions asked. Now, in stark contrast, TCP is connection-oriented. It requires a much stricter, highly secure routing identifier called a four-tuple to ensure that your data goes to the exact right place every single time.
Let's actually look at this TCP four-tuple because honestly, it is brilliant. When a TCP segment arrives, it doesn't just check one thing. It checks 4 pieces of data: the sender's IP, the sender's port, your IP, and your port. So the crucial point is this. Imagine an Apache web server at Amazon handling literally thousands of customers at the exact same time. Every single customer is connecting to the server's HTTP port 80. If Amazon used UDP, all that data would just mix together into a giant mess because every packet just says destination port 80. But because TCP uses all 4 of these identifiers, the server can create a unique socket for every single user, even though they are all knocking on the exact same port 80 door. It flawlessly keeps your shopping cart completely separate from my shopping carts.
Which really leads me to this final thought. When you think about it, from the microscopic toggling of physical logic gates to the complex four-tuple mathematical sorting of TCP sockets, how many millions of times per second is this invisible, absolutely flawless multiplexing and demultiplexing happening inside the very device you're using to watch this explainer right now? It's mind-boggling. So the next time you have a dozen apps open at once, maybe just take a second to appreciate the magnificent traffic cops working tirelessly at the transport layer of your computer. Thank you so much for joining me on this explainer. Keep asking questions, and I'll catch you on the next one.